The cosmos hides ancient ghosts forged in the universe's first second. These are primordial black holes, not the remains of dead stars, but potential relics from the Big Bang itself. We are about to explore 50 mind-bending theories about these cosmic enigmas. You will learn how they might be the invisible dark matter holding galaxies together, or the hidden architects of the entire cosmic web. This journey will challenge your fundamental understanding of space. Could most of the matter in the universe actually be made of black holes? Are we living in a universe built by these primordial seeds? What single idea about the cosmos would you completely rethink if it were proven true? One of the most profound ideas in modern cosmology suggests we have been searching for dark matter in the wrong form. What if the missing mass of the universe is not an exotic, undiscovered particle, but an ancient population of black holes? Primordial black holes could be the invisible material that binds galaxies together. This theory elegantly tackles the mystery of galactic rotation. Stars at the outer edges of galaxies orbit at speeds that should send them flying off into the void. Yet something holds them in, an immense gravitational force from an unseen source. If countless primordial black holes were scattered throughout the galactic halo, their collective gravity would perfectly explain this motion, acting as the hidden anchor for the entire cosmic structure. The beauty of this idea lies in its mass range. For primordial black holes to be dark matter, they could not be the stellar giants we are familiar with. They would need to be far more numerous and elusive, with masses ranging from a small asteroid to a large planet. An asteroid mass black hole would be smaller than a pebble yet contain the weight of a mountain, its gravity subtly tugging on everything around it. After the first gravitational wave detections from merging black holes, this theory exploded back into the spotlight. Some of those colliding objects fell into a mass range that was difficult to explain as the remains of dead stars, reopening the door for primordial origins. This single framework connects two of the universe's greatest puzzles, suggesting the very fabric of the cosmos is woven from the remnants of its violent birth. These cosmic ghosts might also hold the key to another colossal mystery. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These are not just large, they are incomprehensibly huge, weighing in at millions or even billions of times the mass of our Sun. Their existence poses a profound timing problem. We have observed these monsters in galaxies that formed when the universe was less than 1 billion years old, a mere infant in cosmic terms. How did they grow so massive so fast? The slow and steady feeding of a star-sized black hole simply cannot account for such rapid, immense growth in such a short time. This is where primordial black holes offer an elegant solution. Imagine one of these ancient objects, born with the mass of 1,000 suns in the universe's first chaotic moments. As the first galaxies began to coalesce from clouds of dark matter and gas, this heavy primordial seed would naturally sink to the very center of the newborn structure. There, it would find itself at a cosmic feast, surrounded by an unimaginable buffet of gas, dust, and stars. With such a massive head start, this seed black hole could begin accreting material at a ferocious rate, quickly ballooning into the supermassive giant we detect today. The alternative theory suggests these giants formed directly from the collapse of immense gas clouds, but that process is slow and fraught with instability, struggling to explain the speedy appearance of the most ancient supermassive black holes. A heavy primordial seed provides the perfect anchor, a gravitational nucleus that jump-starts the entire growth process. This idea transforms primordial black holes from mere components of dark matter into the fundamental architects of galactic structure, planting the massive hearts around which entire galaxies would eventually form. If true, every giant at the center of a galaxy could trace its lineage back to a single, dense knot in the fabric of the newborn cosmos. But what if the smallest of these cosmic ghosts were also the strangest? We now venture into the territory of the truly minuscule, to a theory involving black holes so small they brush against the very limits of reality. These are the Planck-sized relics, hypothetical primordial black holes with a mass equivalent to the Planck mass. This is the smallest mass a black hole could possibly have according to our current physics, a value so tiny it is about the same as a single grain of pollen. Yet within that microscopic speck would be compressed an unimaginable density, creating an object where the rules of gravity and quantum mechanics collide. This is the frontier where our understanding of the universe breaks down. Such a tiny black hole would be a quantum gravitational object, a laboratory for the laws that govern the fabric of space and time itself. Its existence would be a violent tug of war between two fundamental forces. On one hand, its immense gravity desperately tries to hold it together. On the other, a strange quantum process known as Hawking radiation would theoretically cause it to evaporate. A black hole of this size would not live for billions of years. It might vanish in a flash of energy almost instantly after its birth, its entire life and death playing out in a fraction of a second. Some theories even suggest that the very smallest of these relics could be stable, lasting from the Big Bang until now, drifting through space as eternal, subatomic knots of pure gravity. We have no way to directly detect such an ephemeral object. Its signature would be incredibly faint, a whisper lost in the cosmic background noise. Yet the power of this idea is not in its observability, but in its challenge. The mere theoretical possibility of a Planck-sized black hole forces physicists to confront the deepest questions. What truly happens at the center of a black hole? How does gravity work at the quantum scale? These tiny specks represent the final unknown, the point where our two most successful theories of physics, general relativity and quantum mechanics, meet and fail. They are the ultimate puzzle, hiding the secrets of a unified theory of everything within their hypothetical, fleeting horizons. This ancient light holds its own secrets. The cosmic microwave background is the oldest photograph of our universe, a snapshot from when everything was just a baby, 380,000 years old. This faint glow fills all of space, a nearly uniform tapestry of microwave radiation. But woven into its fabric could be the faint scars of primordial black holes being born. As a black hole spontaneously collapsed into existence in that primordial soup, its sudden, intense gravity would have warped the space around it. Photons from the hot, dense plasma traveling near this newborn singularity would have to climb out of its gravitational well, losing energy in the process. This energy loss would translate into a tiny, cold spot on the otherwise warm background, a subtle dip in temperature against the cosmic canvas. It would be a fossilized shadow, a permanent record of a single, violent birth event from the very dawn of time. But the disturbance would not stop there. The black hole's gravity would also twist the very polarization of this ancient light. Imagine the CMB light as a wave vibrating in a specific direction. As it passes through the warped space around a primordial black hole, that direction could be subtly rotated, leaving a distinct, swirling pattern in the polarization map of the sky. This is the kind of evidence cosmologists are desperately searching for in the exquisitely detailed data from missions like Planck. They are not looking for one obvious, giant cold spot, but for specific statistical anomalies, a certain kind of unexpected pattern scattered across the entire sky that matches the theoretical predictions. Finding even one of these signatures would be a monumental discovery. It would be a direct observational link back to the universe's first second, a smoking gun confirming that primordial black holes are not just a theoretical fantasy but a real component of our cosmic history. This search turns the entire sky into a detective story where the clues are not hidden in the darkness but etched into the oldest light we can see. The silent ripples in space-time detected by LIGO and Virgo might be whispers from the universe's birth. When these observatories first felt the cosmic shudder of colliding black holes, they confirmed a prediction a century in the making. Yet the nature of these dark dancers remains an open question. Some of the merging black holes fell into a puzzling mass range, heavier than what many models predict from the collapse of massive stars. This anomaly sparked a compelling theory. What if these are not the corpses of dead stars, but primordial black holes, finally finding each other after an age of drifting through the dark? The argument for a primordial origin hinges on two key clues: mass and spin. Several of the detected black holes were curiously hefty, sitting in a mass gap that is challenging for stellar evolution to produce. A primordial black hole formed in the chaotic pressures of the early universe would not be bound by the rules that govern a star's death. It could easily form with that specific puzzling mass. The second clue is their quiet rotation. Many of these colliding black holes showed very little spin, meaning they were not twirling rapidly before their final embrace. This is exactly what you would expect from two ancient objects that have spent most of the universe's history wandering independently, only getting gravitationally caught in a slow, stately dance much later. Their merger would be a chance encounter, not the fiery end of a binary star system that lived and died together. Of course, such a dramatic idea faces its own challenges. For two primordial black holes to meet and merge within the age of the universe, they cannot be spread thinly across the vast galactic halo. They would need to be concentrated in incredibly dense clusters where close encounters are frequent. This requirement pushes the theory into a delicate balance. Forming such a dense cluster in the early universe is possible, but it demands very specific and fine-tuned conditions that are still being explored. This is the heart of the debate. Are we seeing the exotic but ultimately stellar end of massive stars, or are we witnessing the final moments of cosmic relics, the direct descendants of the Big Bang itself? The implications of this debate ripple across our entire understanding of the cosmos. If even a fraction of the LIGO-Virgo signals come from primordial black holes, it means these ancient objects are not just theoretical ghosts. They are dynamic players, still colliding and shaping the invisible architecture of our universe today. Each new gravitational wave detection is not just a new data point. It is a potential vote in this ongoing cosmic election, a chance to determine the true identity of the dark giants that roam the void. From the faintest whispers of gravitational waves to the grandest structures in the cosmos, the influence of these ancient objects might be truly universal. The universe is not a random collection of galaxies. Instead, it forms an immense cosmic web, a tapestry of glittering clusters and long, dark filaments stretching across billions of light years. The formation of this colossal architecture is one of cosmology's biggest puzzles. What seeded these structures, guiding matter to gather in such specific web-like patterns? Primordial black holes offer a breathtakingly simple answer. Think of the early universe as a perfectly smooth, dark pond. Now toss in a single, heavy pebble. A primordial black hole with its intense, localized gravity would be that pebble. The moment it forms, it creates a tiny dimple in the fabric of space-time, a gravitational well that immediately begins to pull in the surrounding dark matter and specks of primordial gas. This is the birth of a cosmic seed, the very first clump in a universe that was otherwise almost perfectly uniform. These seeds would not remain isolated. They would act as gravitational anchors, growing steadily as more and more material cascaded into their influence. Over hundreds of millions of years, these small clumps would find each other, merging and colliding to form larger and larger structures. A distribution of the original primordial black holes would directly imprint itself onto the growing cosmic web. Where they were slightly more numerous, vast galaxy clusters would eventually bloom. In the quieter regions, the great cosmic voids would remain. This theory elegantly solves a major problem in our models of the universe. We know that the initial conditions from the Big Bang were incredibly smooth, with only the tiniest of quantum fluctuations. For the massive galaxies we see today to have formed, those fluctuations needed something to amplify them, a catalyst to kickstart the clumping process. Primordial black holes are the perfect candidates for that catalyst. Their powerful, point-like gravity provides a much stronger initial pull than the faint ripples in the dark matter field alone, potentially explaining how the cosmic web formed so quickly and so vividly. In this view, every galaxy cluster, every sprawling filament of the cosmic web, can trace its origin back to a network of these primordial seeds. They are not merely inhabitants of the universe, they are its master builders, the hidden architects that drew the blueprints for everything we see in the night sky. Their gravity wrote the recipe for the cosmos, and we are just now beginning to read it. The brightest objects in the universe may owe their existence to the darkest. Quasars are the furious hearts of distant galaxies, shining with the light of 1 trillion suns from the cosmic dawn. Their incredible power requires a perfect storm, a supermassive black hole feasting on a vast supply of gas at a ferocious rate. But how did this perfect alignment happen so quickly after the Big Bang? A primordial black hole provides the ideal spark for this cosmic inferno. Born with a substantial mass in the universe's first moments, it would not have to slowly build itself up from nothing. From its very beginning, it was a heavyweight contender already possessing the gravity to dominate its surroundings. Its formation mechanism is the key. These black holes did not form in the isolated death throes of stars. They crystallized directly from the densest patches of the hot, young universe, regions that were naturally brimming with raw material. This means a primordial seed would be born right in the middle of a cosmic gas station, an immense reservoir of fuel waiting to be consumed. As it sinks to the center of a proto-galaxy, it begins to feed. Matter spirals in at a dizzying pace, forming a superheated accretion disk that glows with unimaginable intensity. This process is astoundingly efficient at converting mass into pure energy, far more so than nuclear fusion. A primordial black hole engine, with its massive head start and perfect positioning, could achieve this extreme state of activity almost immediately, lighting up as a quasar while the universe was still in its infancy. These beacons are not just spectacular, they are essential tools. The light from quasars illuminates the vast stretches of intergalactic space, allowing us to study the distribution of matter and the evolution of the cosmos itself. Each brilliant point of light could be the signature of an ancient seed, a primordial black hole that grew up to become a lighthouse in the dark, guiding our understanding of the universe's deepest history. That brilliant dawn of the first stars was not the only light transforming the infant cosmos. Another, more powerful force may have been at work in the shadows, one that stripped the universe bare far earlier than expected. This is the epoch of reionization, a universal sea change when the fog of neutral hydrogen atoms was blasted apart into a transparent plasma. The first starlight is often credited with this monumental task, but some models struggle to explain the speed of this transformation. The universe was reionized with a surprising swiftness, and primordial black holes offer a compelling reason why. Imagine the accretion disk around one of these ancient black holes. As gas spirals into the abyss, it is not just heated, it is torn apart with ferocious energy, generating not just visible light, but a torrent of high-energy ultraviolet and X-ray radiation. This is the key difference. The ultraviolet light from the very first stars was relatively soft, often absorbed by the surrounding hydrogen before it could travel far. But the X-rays from a primordial black hole's disk are hard and penetrating. A single such photon carries enough punch to rip through vast clouds of neutral hydrogen, knocking electrons loose from their atoms with ruthless efficiency. One primordial black hole, shining as a microquasar, could therefore ionize a bubble of space thousands of times larger than a cluster of the earliest stars. Scattered across the early universe, a population of these objects would act like a network of powerful lighthouses, their penetrating beams clearing the cosmic fog in a patchwork of transparent bubbles. These bubbles would then grow and merge, accelerating the entire process of reionization and giving the universe its transparency far sooner than starlight alone could manage. This theory paints a new picture of the cosmic dawn, not just as a time of the first gentle starlight, but as an era also illuminated by the violent, piercing glare of ancient black holes, their hidden energy fundamentally reshaping the universe for everything that was to come. These invisible cosmic ghosts could be caught in the act of bending starlight. The phenomenon of gravitational microlensing provides a direct way to hunt for isolated primordial black holes drifting silently through the galactic halo. It works because gravity warps the very fabric of space. When one of these dark, compact objects passes almost directly in front of a distant background star, its gravitational field acts like a tiny, invisible lens. This lens briefly focuses and amplifies the star's light, causing it to brighten in a very specific way. The star appears to flare up over a period of hours, days, or weeks, then just as smoothly fades back to its normal brightness. The duration of this event is a direct clue to the mass of the invisible lens. A brief, sharp brightening points to a small, asteroid mass object. A longer, more drawn-out event suggests the lens has the mass of a planet or more. This is the perfect method to search for primordial black holes in that crucial planetary mass range, objects that are too small to form from stars and too faint to emit any light of their own. Dedicated sky surveys have turned this idea into a relentless, automated hunt. Projects like the Optical Gravitational Lensing Experiment, known as OGLE, and the Hyper-Subprime CAM survey scan millions of stars night after night, their electronic eyes searching for these telltale flashes. They are not looking for one single event, but for a statistical pattern, a specific rate of these microlensing occurrences that cannot be explained by ordinary, visible objects like faint stars or rogue planets. Finding a population of these isolated, invisible lenses would be a monumental discovery. It would be direct, observational proof that a hidden army of massive, compact objects, perfectly consistent with primordial black holes, is drifting through our galaxy. Each brief, silent flare in the data is a potential ghost signature, a momentary distortion in the path of a photon that traveled for thousands of years, only to have its final moments bent by an ancient relic from the dawn of time. One of the most dramatic fates for a primordial black hole is written in the laws of quantum mechanics. Hawking radiation is the theoretical process by which black holes can slowly lose mass and evaporate over cosmic time. For a stellar mass black hole, this process is so slow it is utterly negligible. But for a small primordial black hole, it is everything. A black hole with a mass less than a large mountain would be in its death throes right now. Its final moments would not be a quiet fade to black, but a cataclysmic release of energy. As the black hole shrinks, the rate of evaporation accelerates exponentially. In the last second of its life, it would unleash a torrent of high-energy particles and an intense flash of gamma rays, a final firework visible across the universe. This is not a gentle glow, it is a sudden, powerful burst. The hunt for these specific signals is a primary mission for instruments like the Fermi Gamma Ray Space Telescope. Astronomers meticulously scan the sky for brief, sharp gamma-ray flashes that cannot be explained by more common events, like merging neutron stars. They are searching for the unique fingerprint of a primordial black hole blinking out of existence. So far, no confirmed signal has been found. This absence places crucial limits on how many of these small, evaporating black holes could be floating in our cosmic neighborhood. But the search continues because the prize is unparalleled. Detecting one of these Hawking radiation fireworks would be a 2-for-1 discovery of historic proportions. It would confirm the existence of primordial black holes beyond any doubt, and simultaneously provide the first experimental proof for Hawking radiation itself, validating a cornerstone of theoretical physics that has stood for decades without direct observation. Every unclassified gamma-ray burst is a moment of possibility, a chance that we are witnessing the last gasp of a cosmic ghost from the dawn of time. Our very existence rests on a profound cosmic imbalance. We live in a universe made almost entirely of matter, but our best theories insist the Big Bang should have created equal amounts of matter and antimatter. Something must have tipped the scales, a process known as baryogenesis that left behind the stars, planets, and us. One of the most speculative theories points the finger at evaporating primordial black holes. As these tiny black holes neared the end of their lives through Hawking radiation, they would have become incredibly hot, acting as powerful particle accelerators on a microscopic scale. The key to the theory lies in a subtle asymmetry in the laws of physics called CP violation. This is the idea that the universe treats particles and their mirror image antiparticles slightly differently. An evaporating primordial black hole, under the intense influence of its own gravity and temperature, could have exploited this asymmetry. It might have emitted just a few more matter particles than antimatter particles in its final furious burst. On its own, a single black hole's contribution would be negligible. But if countless trillions of these objects evaporated in the universe's first second, that tiny bias would have been amplified across the entire cosmos. Each dying black hole would have been a minuscule factory, adding one more brick of matter to the cosmic pile than antimatter. Overwhelmingly, this process could have generated the net surplus of matter we see today, transforming a symmetrical primordial soup into the lopsided, material-rich universe we call home. This idea places these ancient objects at the very heart of our own origin story. Without a population of primordial black holes acting as catalytic engines, the universe might have remained a perfect, balanced void, with all matter and antimatter having annihilated each other long ago, leaving behind nothing but a faint sea of radiation and no one to witness it. Another leading candidate for dark matter is not a black hole at all, but a ghostly particle known as the action. This hypothetical entity was first proposed to solve a deep puzzle in particle physics, but it has since become a prime suspect for the universe's missing mass. Now, a fascinating theory suggests that primordial black holes and actions are not rivals, but partners in crime, with the black holes acting as powerful factories for these elusive particles. The connection begins with the intense gravitational environment surrounding a primordial black hole. In a process called superradiance, a spinning black hole can effectively transfer its own rotational energy to a surrounding cloud of quantum particles. Imagine a spinning black hole as a massive top and the action as a wave of energy lapping at its edges. If the wave's frequency matches the black hole's spin in just the right way, the black hole can amplify the wave, pumping energy into it until a vast, invisible cloud of actions forms around the singularity. This cloud would be immense, potentially spanning distances far greater than our solar system, all bound by the black hole's gravity. But the production does not stop there. The violent conditions of the early universe could have triggered another mechanism. As a primordial black hole formed and evaporated, its wildly fluctuating gravitational field might have directly converted raw energy into actions, sprinkling them across the cosmos. This turns each black hole into a prolific generator, potentially creating the very dark matter that then cloaks it. The beauty of this partnership is that it offers a way to detect both mysteries at once. A primordial black hole enshrouded in a dense action cloud would be a very different object gravitationally. The cloud itself would have mass, subtly altering how the black hole interacts with its environment and, most importantly, how it merges with another black hole. When two such cloud-wrapped black holes spiral together, their action halos would interact long before the black holes themselves collide. This interaction would produce a unique, oscillating fingerprint in the gravitational wave signal, a specific hum or beat in the data recorded by observatories like LIGO. Detecting this signature would be a monumental double discovery. It would not only confirm the existence of primordial black holes, but also simultaneously identify the action as the constituent of dark matter, solving two of the universe's greatest puzzles with a single, elegant observation. This theory weaves together the physics of the very large and the very small, suggesting that the darkest objects in the cosmos might be the key to illuminating the true nature of the invisible universe. Another origin story for these cosmic ghosts lies in the cracks of reality itself. Beyond simple density fluctuations, primordial black holes might have been forged from the violent collapse of cosmic strings. These are not strings in any ordinary sense, but hypothetical, incredibly dense flaws in the fabric of space-time, one-dimensional scars left over from a phase transition in the universe's first moments. Picture the early cosmos cooling from an indescribably hot and symmetric state, like water freezing into ice. As it cooled, the fundamental fields that govern reality might have settled into their new state imperfectly, creating tangled, thread-like defects of trapped energy. A cosmic string would be a filament of pure gravity, thinner than a proton but so dense that a single inch of it could weigh more than Mount Everest. If such a string existed, it would not lie still. Under its own immense tension, a loop of cosmic string could whip through space, oscillating wildly. Under the right conditions, this frantic motion could become so extreme that the loop would collapse in on itself. The energy concentrated within that tiny, vanishing point would be so immense that it would inevitably wrap space into a knot of infinite density, spontaneously birthing a black hole. This process offers a unique prediction. Unlike black holes formed from random density bumps, which could have a wide range of masses, the progeny of cosmic strings would be different. The mass of the resulting black hole is tied directly to the length of the string loop that collapsed. This creates a very specific mass spectrum for these black holes, a distinct fingerprint etched into their population. We would not expect to find a smooth distribution of all sizes, but perhaps a series of sharp peaks at certain masses, a cosmic barcode revealing their stringy ancestry. Finding such a pattern in the black holes we detect through gravitational waves or microlensing would be like finding a manufacturer's stamp on a mysterious artifact. It would point unequivocally to this exotic birth mechanism, proving that the universe's first structures were not just clumps of matter, but literal defects woven into the expanding fabric of space-time. The very expansion of the universe might have sown the seeds for these dark ghosts. Our leading theory for the birth of primordial black holes takes us back to the inflationary epoch, a dizzying moment of super-fast expansion that happened in the first fraction of a second after the Big Bang. During this brief but universe-defining instant, space itself expanded faster than the speed of light, stretching a subatomic speck into a volume larger than our entire observable cosmos. This process did not create a perfectly smooth void. Instead, it was a quantum foam, bubbling with tiny, random fluctuations in energy and density. These fluctuations were the raw material for everything to come. As inflation stretched the fabric of space, it also stretched these quantum ripples, magnifying them from the microscopic to the cosmic scale. Most of these stretched ripples were small, the gentle hills and valleys that would later become the slight temperature variations we see in the cosmic microwave background. But what if some of those initial quantum bumps were not so gentle? Imagine a particularly large peak in this quantum landscape, a chance concentration of energy so dense it stood out from the rest. As inflation blew up the universe, this large peak was stretched into a massive, region-sized overdensity. When the frantic expansion of inflation finally ended, the normal, slower expansion of the Big Bang took over. At that critical moment, gravity reasserted its dominance. That large, dense region, now weighing perhaps as much as a planet or a star, would have found itself under its own immense weight. There was no nuclear fusion to push back, no internal pressure to support it. It would have simply collapsed directly and completely, wrapping a region of space so tightly that a black hole was the only possible outcome. This theory provides a direct and elegant link between the most microscopic laws of physics and the macroscopic objects we hypothesize today. The properties of the resulting primordial black holes, their masses and their abundance, become a direct fossil record of inflation itself. By studying these potential black holes, we are effectively reading the magnified signature of the universe's first quantum tremors, a permanent imprint of the forces that shaped our entire reality. The title primordial might not always mean first. A compelling alternative suggests these ancient black holes are not relics of the Big Bang itself, but the tombstones of the universe's very first stars. These pioneer suns, known as population 3 stars, were unlike anything that exists today. Born from the pristine hydrogen and helium forged in the Big Bang, they contained no heavy elements to help them regulate their burn. This purity allowed them to grow to staggering sizes, hundreds of times more massive than our own sun. Such a colossal star lives a spectacularly short and violent life, burning through its nuclear fuel in just a few million years. Its end would not be a typical supernova. With no complex elements in its core, the internal physics could play out differently. Instead of exploding, the entire star might simply give way, collapsing directly into a black hole without a final, brilliant flash. It would just vanish, leaving behind a silent gravitational pit where a giant star once shone. This theory elegantly redefines what we mean by primordial. These black holes would not be from the universe's first second, but from its first few hundred million years. That is still incredibly ancient, a time so remote that calling them primordial feels entirely justified. They would be among the first black holes to exist, even if they were not the absolute first. This origin story solves a key problem. It provides a natural and efficient factory for a population of early black holes with a specific mass range, perfectly suited to become the seeds for future supermassive giants. These first stellar remnants would have been scattered throughout the infant cosmos, each one a heavy anchor ready to gather gas and begin building a galaxy. The distinction is subtle but profound. Are we seeing the direct handiwork of the Big Bang's chaos, or are we witnessing the silent fallout from the first cosmic dawn, the dark legacy of the first generation of stars to ever grace the universe? These cosmic messengers could carry passports from entirely different realities. The concept of a multiverse suggests our universe is just one bubble in a vast, frothing cosmic foam, with other universes constantly budding into existence, each with its own unique laws of physics. Within this grand picture, primordial black holes take on an even more profound role. They might not be products of our universe's birth at all, but artifacts from a neighboring cosmos. Imagine two of these universe bubbles drifting through the higher dimensional void. If they were to gently collide, the energy released at their boundary would be astronomical. That concentrated point of impact could easily warp space-time so severely that it pinches off, creating a black hole that is then deposited into our cosmic domain. This object would be a true alien, a knot of space-time that formed under the physical laws of another reality. Its properties could be wildly different from anything our universe could produce naturally. We might detect a primordial black hole with a mass that is simply impossible according to our models of inflation or stellar collapse. Perhaps it would have a strange charge or a quantum signature that defies explanation. Finding such an oddity would be like an archaeologist discovering a perfectly machined steel tool in a Stone Age dig site. It would be an artifact that clearly does not belong, pointing unequivocally to an intelligence or a process from beyond our own world. This transforms the search for primordial black holes from a hunt for ancient relics into a potential first contact with another cosmic realm. They would be the ultimate messengers, silent and dark, yet carrying within their simple gravitational field the revolutionary proof that our universe is not alone. Each one drifting through the galactic halo could be a souvenir from a collision with another reality, a permanent reminder that the cosmos is far stranger and more vast than we ever dreamed. Strange orbits at the solar system's edge hint at a hidden world, but the culprit may not be a planet at all. Far beyond Neptune, in the cold, dark realm of the Kuiper Belt, a collection of icy objects follows clustered, tilted paths that are difficult to explain by chance alone. Their unusual trajectories seem to be shepherded by the persistent gravitational tug of something massive lurking in the shadows. This hypothetical object has been dubbed Planet 9. Yet a more exotic possibility exists. The gravitational shepherd out there could be a primordial black hole, roughly the mass of Earth but compressed into a sphere no larger than a grapefruit. A captured primordial black hole would exert the exact same gravitational influence as a rocky planet, perfectly explaining the warped orbits of those distant ice worlds without ever being seen. The search for this dark interloper relies on clever, indirect methods. Since it emits no light, astronomers cannot simply point a telescope and find it. Instead, they look for the fleeting signatures of its destructive presence. One method involves the potential for dark matter annihilation. If dark matter consists of theoretical particles like WIMP, a primordial black hole's intense gravity could gather a dense halo of these particles around it. When two WIMP collide within this halo, they could annihilate each other in a flash of gamma radiation. Our instruments would see this as a strange, moving point of light drifting slowly against the fixed stars. Another tactic is to watch for accretion flares. Even in the near-perfect vacuum of the outer solar system, a tiny amount of diffused gas and dust exists. As this material is pulled toward the black hole, it would compress and heat up, potentially glowing in X-rays before vanishing across the event horizon. Telescopes scan the sky for these brief, unexplained X-ray flashes, tracking any that appear to move with the slow, deliberate pace of an object bound to our sun. Finding such an object in our own cosmic backyard would be a discovery of unparalleled significance. It would mean that one of the most ancient relics of the Big Bang is not in some distant galaxy, but is right here, a permanent dark member of our solar family. This would provide a unique, close-up laboratory to study primordial black holes and potentially solve two mysteries at once, revealing the nature of the phantom perturbing the Kuiper Belt while offering a tangible piece of the universe's primordial past. The universe is full of sudden, brilliant screams. Fast radio bursts are among the most enigmatic, intense flashes of radio waves that appear for mere milliseconds and then vanish, often without a trace. These cosmic fireworks release more energy in a single blink than our sun does in 3 days, and their origin has been one of astronomy's most compelling puzzles. One of the most daring theories suggests these events are not the death cries of stars, but the violent wake of a primordial black hole passing through a cosmic minefield. Imagine an asteroid-mass black hole, a dark, mountain-sized relic drifting silently for eons. Its journey eventually takes it through the extreme environment surrounding a neutron star, a city-sized stellar corpse with a magnetic field so powerful it can shred atoms. As the black hole pierces this magnetosphere, it acts like a bullet tearing through a supercharged electrical grid. The sudden, catastrophic disruption of the magnetic field lines would trigger a colossal short circuit, unleashing a titanic shockwave of radio energy. In an instant, the silent passage of a dark ghost is translated into a brilliant, observable flash, a signal we detect as a fast radio burst. This model elegantly explains the key characteristics of these mysterious events. The millisecond duration perfectly matches the brief moment it would take for the black hole to cross the neutron star's magnetosphere. The incredible energy output aligns with the vast reserves of magnetic energy available to be unleashed. And the one-off nature of many bursts fits the idea of a chance encounter, a single, random trigger passing through a sensitive region. This transforms our understanding of these cosmic flashes. They are not necessarily the central engines of distant objects, but the side effects of an invisible, ancient object briefly brushing against the visible universe's most extreme physics. Each sudden burst of radio noise could be the signature of a primordial black hole announcing its presence, not with a whisper, but with a spectacular, accidental firework. The silent drift of a primordial black hole could trigger the very explosions that illuminate the cosmos. Among the most vital tools for measuring the universe are Type Ia supernova, the brilliant, predictable detonations of white dwarf stars. Astronomers rely on them as standard candles, cosmic mile markers whose consistent peak brightness allows us to gauge vast distances. Yet the precise trigger for these cataclysms has remained a subject of intense debate. One compelling theory suggests a dark interloper is the culprit. Imagine a white dwarf, the Earth-sized ember of a sun-like star, composed of degenerate carbon and oxygen and poised on the edge of stability. It is a stellar bomb waiting for a spark. Now introduce a single asteroid mass primordial black hole. This tiny, incredibly dense object would not be captured by the star. Instead, it would pass straight through, a dark bullet piercing the stellar interior. The violence of this passage is the key. As the black hole tunnels through the dense core of the white dwarf, its immense gravity does not just pull matter in. It violently compresses the degenerate material along its path, creating a superheated, high-pressure wake. This is not a gentle heating, but a sudden, traumatic shock. In the extreme conditions of this shock front, nuclear fusion ignites with ferocious speed. Unlike the steady fusion in a normal star, this is a runaway chain reaction with no outward pressure to contain it. The fusion front races through the white dwarf's core in mere seconds, overwhelming the star's gravity and tearing the entire object apart in a titanic thermonuclear explosion. This mechanism offers a beautifully simple solution to a long-standing puzzle. The standard model for a Type Ia supernova requires a white dwarf to slowly accrete mass from a companion star until it reaches a critical threshold. But we observe these explosions in places where no companion star is evident. A primordial black hole provides a solitary trigger, a random event that could occur to any isolated white dwarf in the galaxy. The resulting explosion would be indistinguishable from one caused by accretion, creating the perfect standard candle astronomers depend on. This idea weaves primordial black holes directly into the tools we use to map the cosmos. The very explosions that revealed the accelerating expansion of the universe, hinting at the existence of dark energy, might themselves be sparked by the universe's most ancient ghosts. Each brilliant supernova could be the final, violent signature of a dark particle's chance encounter, a cosmic collision that turns a dying star into a beacon for measuring the void. A neutron star is the densest object we can directly observe, a city-sized orb of pure nuclear matter so compact that a single teaspoon would weigh 1 billion tons. Yet even this cosmic fortress has a theoretical weakness, a ghost that could devour it from within. If a primordial black hole, even one with just the mass of a mountain, were captured by a neutron star, it would initiate a slow and inevitable destruction. The process begins with a gravitational dance. As the black hole passes near the ultra-dense star, it loses energy through dynamical friction, a cosmic braking effect caused by its gravitational pull on the surrounding material. This gentle but persistent drag would slowly spiral the black hole down through the neutron star's outer layers, like a lead weight sinking through an ocean of molasses. The journey to the core could take 1 million years, a silent, creeping descent. Once it reaches the very center, the true consumption begins. nestled in the heart of the star, the black hole starts to accrete the neutron-rich material directly onto its event horizon. This is not a fast process, but a steady, unstoppable one. The black hole feeds, growing in mass and its gravitational influence. As it eats, it hollows out the neutron star from the inside. The star's own immense gravity, which was the only thing holding it together, now works against it, pushing more and more material toward the central parasite. The final act of this cosmic drama would be a spectacular one. When the black hole has consumed enough of the star's core, the entire structure becomes unstable. The remaining outer layers, no longer supported by a solid core, would collapse inward in a catastrophic implosion. This sudden, total collapse would ring the fabric of space-time, producing a unique, low-frequency burst of gravitational waves. Simultaneously, the violent compression and destruction of the neutron-rich matter would release an unimaginable flood of neutrinos, ghostly particles that barely interact with anything. This 1-2 punch of a gravitational wave chirp and a neutrino burst would be a smoking gun, a signature unlike any other event in the cosmos. This theory also offers a solution to a curious astronomical absence. In the dense stellar environments of some galactic centers, we expect to find many old neutron stars, yet they seem to be missing. If primordial black holes are common in these regions, they could have systematically captured and consumed these stellar remnants over billions of years, leaving behind only dark, quiet singularities where pulsars should be. The silent, patient work of a cosmic ghost could have cleaned an entire region of space, leaving behind only a gravitational memory of the stars that once were. The most energetic particles in the universe rain down on us from the depths of space. These are ultra-high energy cosmic rays, atomic nuclei traveling at a fraction of light speed, each one carrying the punch of a professionally thrown baseball. For decades, their origin has been a profound mystery, as no known object in our galaxy seems powerful enough to launch them. Primordial black holes may be the universe's hidden particle cannons, operating on a principle far more violent than any human-made accelerator. The engine for this incredible feat is the chaotic environment just outside the event horizon. When a primordial black hole drifts through a cloud of interstellar gas, it does not simply swallow matter quietly. Material is pulled into a frantic, whirling orbit, forming a superheated accretion disk. Within this maelstrom, unimaginably powerful magnetic fields are generated, tangled and stretched like cosmic rubber bands. Charged particles, such as protons or atomic nuclei, become trapped in these magnetic whirlpools. They are whipped around faster and faster, gaining energy with each pass, as if caught in an immense natural slingshot. Occasionally, these magnetic fields snap, reconnecting in a violent event that flings the trapped particles outward. This process, combined with immense shock waves within the swirling disk, can accelerate these particles to over 99.9% the speed of light, imparting energies that dwarf anything our most powerful colliders can produce. A single, modestly sized primordial black hole could act as a relentless cosmic ray factory. Now consider a population of these objects scattered throughout the galactic halo. Each one is a silent, dark engine, constantly firing off volleys of these ultra-high energy particles in random directions. Some of those particles, after traveling for millions of years across the galaxy, would inevitably intersect with Earth's atmosphere. When they do, they create a spectacular air shower, a cascade of secondary particles that our detectors on the ground can see. This theory elegantly solves the puzzle of origin. These primordial accelerators are dark, widespread, and possess the perfect combination of intense gravity and magnetic chaos to explain the extreme energies we observe. They are the unseen snipers in the cosmic arena, and the rare, mysterious particles that strike our sky could be the spent bullets from their eternal, hidden war. These silent relics could be the ultimate cosmic time capsules, A primordial black hole is not just an object, it is a moment frozen in time, a perfect snapshot of the universe's most extreme infancy. Formed in the first chaotic second after the Big Bang, its very existence is a direct consequence of the laws of physics as they were at that exact instant. If we could somehow peer past its event horizon, we would not be looking into empty darkness, but into a vault containing pristine information about the primordial cosmos, information that has been erased everywhere else in the universe. Within that gravitational prison, the conditions of that first fraction of a second could be perfectly preserved. We might find relics of grand unified theories, the hypothetical era when the fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force were one and the same. As the universe expanded and cooled, these forces split apart, a process that forever changed the fabric of reality. But inside a primordial black hole, that split may have never completed. The state of that perfect unity could be locked away, a frozen memory of when the cosmos was simpler and more symmetric. This vault could also hold evidence for physics we can only dream of. The intense energies at which these black holes formed are far beyond what any particle collider on Earth can ever hope to achieve. They are energies where exotic phenomena become possible. Some theories suggest the universe has more than the three spatial dimensions we experience. At those incredible energies, these extra dimensions might have been significant, curling and folding in ways that left a permanent imprint on any object born there. A primordial black hole could be a knot where a tiny piece of a higher dimension is permanently trapped, its geometry woven into the singularity's heart. Other speculative ideas, like supersymmetry, which proposes a partner particle for every known particle, might have left their mark there too. The problem, of course, is the event horizon itself. It is the ultimate barrier shielding these cosmic secrets from our view. According to our current understanding, anything that crosses that boundary is lost to us forever, its information seemingly destroyed. This is the famous black hole information paradox, a deep conflict between general relativity and quantum mechanics. Yet, if we could ever solve that paradox, if we could find a way to decode the information a black hole holds, then these primordial ones would be the most valuable prizes of all. They would offer a direct line of sight back to the beginning of everything, a chance to read the universe's original, unaltered blueprint. Each one is a message in a bottle from the dawn of time, and we are only just learning that the bottle exists. These tiny cosmic knots are nature's ultimate experimental chambers. A primordial black hole the size of an atom places us at the very frontier of physics, where our two greatest theories of the universe meet and falter. On one hand, we have general relativity, which masterfully describes the gravity of planets, stars, and galaxies. On the other, we have quantum mechanics, the bizarre and brilliant rules that govern the world of atoms and particles. For a century, these two frameworks have refused to unite, creating the most significant rift in modern science. But a microscopic primordial black hole is the one place where both sets of laws are screamingly relevant at the same time. Its immense, crushing gravity is pure general relativity, warping space into a closed trap. Yet its vanishingly small size is the domain of quantum uncertainty, where particles can pop in and out of existence at the very edge of its horizon. This violent overlap makes it a perfect natural laboratory, a place where the universe itself is running experiments we could never hope to replicate on Earth. The entire life cycle of such a black hole is a quantum gravitational play. Its birth from a quantum fluctuation in the early universe is the first act. Its evaporation through Hawking radiation is the final, dramatic scene where quantum effects ultimately overcome gravitational binding. By studying these processes, even theoretically, we are looking for the subtle cracks in our current models, the places where relativity and quantum mechanics give slightly different predictions. For instance, what exactly happens at the singularity at the black hole's center? Our current laws break down completely there, predicting a point of infinite density. A theory of quantum gravity would smooth out that infinity, describing the true nature of that central point, perhaps as a dense knot of space-time itself. The information that seems to vanish into a black hole is another crucial clue. Quantum mechanics insists that information is never truly lost, yet general relativity suggests it is erased forever behind the event horizon. This is the famous black hole information paradox. The way a tiny primordial black hole evaporates and disappears could hold the answer. Does the information it swallowed leak back out in the final flash of Hawking radiation, or is it truly gone? Resolving this would not just be an academic victory, it would force us to rewrite the fundamental rules of reality. Every hypothesis about these smallest black holes is a potential stepping stone toward the holy grail of physics. A single, elegant theory of everything that can describe the cosmos from the vastest galaxy cluster to the tiniest vibrating string. These ancient relics are not just fossils, they are messengers carrying within their simple, dark hearts the secret to unifying our understanding of the universe. The first stars in the cosmos may have been fueled by darkness itself. A dark star is a theoretical giant from the universe's infancy, a behemoth that shone not with the nuclear fire of our sun, but with the gentle, pervasive heat of annihilating dark matter. This strange power source would have allowed such a star to grow to staggering proportions, potentially reaching millions of times the mass of our sun and shining with a cool, red glow for millions of years. For this to work, the dark matter needed a way to release its energy, and primordial black holes provide the perfect catalyst. Imagine a dark star's core not as a site of fusion, but as a trap filled with countless asteroid mass black holes. These ancient specks would continuously accrete the surrounding dark matter particles. As the particles cross the event horizon, their immense gravitational energy would be converted into heat, warming the star from the inside out. At the same time, the tiniest of these black holes would be evaporating via Hawking radiation, adding their own faint quantum glow to the internal furnace. This combined output of accretion heat and Hawking radiation would create a stable, low-temperature energy source, preventing the star from ever triggering conventional nuclear fusion. Its structure would be utterly alien, puffy and diffuse, more like a vast, warm cloud than a dense, fiery ball of plasma. The life cycle of a dark star would be a slow, steady burn, lasting far longer than any fusion-powered star. Its eventual fate, however, would be a direct consequence of its dark heart. Once it exhausted the local dark matter fuel, or if the internal black holes merged into a single, dominant singularity, the entire structure could collapse directly into a supermassive black hole. This provides a direct and elegant pathway from the first stars to the giant black holes we find at the centers of galaxies today. The dark star theory beautifully links the universe's most elusive substance to its most brilliant structures, suggesting that the first light in the cosmos was a ghostly radiance, born from the slow consumption of the dark ghosts themselves. The very heart of our galaxy is whispering in gamma rays. For years, telescopes have detected a mysterious, diffuse glow emanating from the Milky Way's core, an excess of high-energy light that defies easy explanation. The leading theory points to dark matter, suggesting that hypothetical particles are colliding and annihilating each other in a constant, silent fireworks display. But there is another, equally compelling possibility. What if this gamma-ray haze is not from particles at all, but from the final breaths of countless ancient black holes? A dense, swirling cluster of primordial black holes gathered at the galactic center could be the true source of this enigmatic signal. Each tiny black hole in this dark multitude would be a powerful engine of radiation. Through Hawking radiation, the smallest among them would be in their death throes, evaporating in a final, brilliant flash of gamma rays. The larger ones, though stable, would still leave a mark. As they drift through the thin haze of interstellar gas at the galactic center, Their immense gravity would pull material inward, compressing and heating it until it glows fiercely with X-rays and gamma radiation before vanishing over the event horizon. This collective output from millions of these dark objects could perfectly mimic the smooth, spherical pattern of gamma rays we observe, creating a ghostly glow that looks exactly like a dark matter signal. This idea elegantly sidesteps the need for a new, undiscovered particle. Instead, it uses known physics, applying the theoretical principles of Hawking radiation and accretion to a population of objects we already have reason to suspect exist. The galactic center is a natural gravitational trap, a place where wandering primordial black holes would have accumulated over billions of years, drawn in and held captive by the immense pull of the central supermassive black hole. Their presence there would create the perfect conditions for this alternative explanation. The beauty of this theory is its testability. If the gamma rays come from dark matter particle annihilation, the signal should be very specific and sharp. But if they are produced by a population of evaporating and accreting black holes, the energy spectrum of the light might have subtle, telltale bumps and a broader shape that future, more sensitive telescopes could identify. We are therefore faced with two profound possibilities for the same mysterious glow. Is it the signature of the universe's most elusive particle, finally revealing itself, or is it the collective death rattle of the universe's oldest ghosts, shining from the dark heart of our own home galaxy? That faint cosmic hum is the soundtrack of a universe in motion. Pulsar timing arrays have given us ears to listen to the gravitational wave background, a low-frequency drone permeating all of space. This signal is often interpreted as the stately, slow dance of countless pairs of supermassive black holes, orbiting each other in the hearts of distant galaxies over billions of years. Yet another, more ancient source could be contributing to this chorus. Imagine the early universe filled with a dense sea of primordial black hole binaries, pairs that were gravitationally bound from the moment of their birth. As the cosmos expanded, these couples would slowly spiral inward, their orbits decaying over eons. The collective emission from countless such mergers, happening across all of cosmic history, would create a persistent background rumble of gravitational waves. This is not the loud, distinct chirp of a single LIGO detection, but a diffuse sea of whispers, all adding up to the hum we detect today. This primordial explanation is compelling because it requires no late-stage galaxy formation or complex binary capture. The pairs were created in the initial chaos, and their mergers have been providing a steady, underlying beat to the universe ever since. The challenge lies in the details. Could a population of these early binaries survive for so long without being torn apart by interactions with other matter or with each other? And would their combined signal match the specific frequency and amplitude that the pulsar timing arrays are now measuring? Researchers are actively modeling this scenario, running simulations to see if the primordial black hole narrative can produce the exact soundtrack we are hearing from the depths of space. The implications are staggering. If even a portion of this background hum comes from these ancient pairs, it means the early universe was far noisier than we thought, ringing with the collisions of its first dark inhabitants. Our universe might be living on borrowed time, perched precariously on a cosmic ledge. The laws of physics we rely on, from gravity to the nuclear forces, could be temporary, a local arrangement that is not the most stable state possible. This is the unsettling premise of the false vacuum theory. Think of our universe as a valley in a vast cosmic landscape, but not the lowest valley. We are in a false vacuum, a state that seems stable for now, but a more stable, true vacuum state exists at a much lower energy level somewhere else in the cosmic terrain. The terrifying part is that a quantum event could nudge our local patch of space over the ledge, initiating a catastrophic phase transition called vacuum decay. A primordial black hole could be the very thing to provide that fatal nudge. Its immense, point-like density warps spacetime so severely that it might create the perfect conditions for a quantum bubble of true vacuum to nucleate right at its event horizon. This would not be an explosion in the traditional sense. It would be a rewriting of reality itself. The moment that bubble forms, it would begin to expand in all directions at the speed of light. There is no warning, no sound, and no escape. The boundary of this bubble is a wall of fundamental change. As it passes through space, it does not destroy matter by force, but by redefinition. The laws of physics inside the bubble are different. The rules that allow atoms to form, that permit chemistry and life, simply cease to exist. Everything we know, every star, every planet, every memory, would be instantly and permanently erased, transformed into something entirely new and unrecognizable according to the new, stable laws of the true vacuum. This is not a theory about the end of the world, but the end of physics. The expansion would be relentless and universal, a sphere of oblivion growing at light speed until it has consumed the entire cosmos. The trigger could have already happened somewhere in the distant universe, and the sphere of annihilation could be on its way to us right now, with no way for us to see it coming. A single ancient black hole, a relic from the first second, could hold the seed of the ultimate cosmic doom, a silent countdown to the moment it rewrites existence itself. A black hole's evaporation poses a fundamental threat to our understanding of reality itself. This is the heart of the black hole information paradox, and primordial black holes are its perfect and perhaps only test subjects. Stephen Hawking's revolutionary calculation showed that black holes are not truly black, but slowly leak radiation and fade away. For a massive stellar black hole, this process takes longer than the current age of the universe, making it a purely theoretical concern. But a small primordial black hole could evaporate completely in a flash, forcing the paradox into the open. The crisis is this: quantum mechanics, the rulebook for the universe, states that information is never destroyed. Every particle that falls into a black hole carries information about its properties, its spin, its mass, its identity. According to Hawking's early work, this information is scrambled and lost forever when the black hole finally vanishes. The radiation it emits is purely thermal, random noise that carries no data about what was consumed. It would be like burning a complex, detailed encyclopedia and claiming the heat and smoke rising from the ashes contain no trace of the words and pictures inside. This is a direct violation of a core principle of quantum physics. The implications are staggering. If information can be lost, then the universe is fundamentally unpredictable, and the past cannot be reliably reconstructed from the present. The entire logical foundation of physics would crack. Primordial black holes are the key to a potential resolution because their entire life cycle, from birth to explosive death, plays out on a human timescale. If we could ever detect one in its final moments of evaporation, we could analyze the precise spectrum of its Hawking radiation. The critical question is it truly random and featureless, or are there subtle, hidden correlations in the particles it emits, a coded message revealing what fell in? Finding even a single, tiny deviation from pure randomness would be a monumental discovery, proving that information does, in fact, escape. It would validate modern theories like the holographic principle, which suggests that all the information about what falls into a black hole is not lost inside, but is somehow encoded on its two-dimensional surface like a cosmic fingerprint and is slowly released back into the universe. Observing a primordial black hole's death would transform this philosophical debate into experimental science, giving us a direct window into the quantum nature of space-time and potentially saving the logical consistency of the universe. The event horizon of a black hole may be more than a point of no return. It could be a cosmic hard drive encoding the secrets of everything that falls inside. This is the essence of the holographic principle, one of the most mind-bending ideas in theoretical physics. It suggests that our perception of a three-dimensional universe might be an illusion, a magnificent hologram projected from information stored on a distant two-dimensional surface. The entire cosmos, with all its stars, planets, and people, could be akin to a three-dimensional movie projected from a flat screen. Primordial black holes, with their simple and well-defined event horizons, are the perfect theoretical laboratories to test this radical concept. Their spherical surfaces provide a clean, finite boundary where physicists can calculate exactly how information might be stored. Every particle swallowed by a black hole, according to this principle, does not vanish into a singularity. Instead, its information is smeared and perfectly encoded onto the event horizon itself, imprinted in tiny, Planck-sized pixels on that spherical surface. The evaporation of a small primordial black hole is where this theory faces its ultimate test. As the black hole emits Hawking radiation and shrinks, what happens to all that encoded information? Does it get destroyed, violating a fundamental law of physics, or is it somehow carried away by the escaping radiation? Solving this puzzle for a primordial black hole would be like cracking the universe's source code. It would tell us if reality as we experience it is fundamental, or merely a shadow cast by a deeper, simpler layer of existence operating at the very boundaries of space. Hidden dimensions could be curled up all around us, too small for our eyes to see. String theory and other bold attempts to unify physics suggest our universe may have more than the three spatial dimensions we experience. We might be living in a cosmic landscape where extra dimensions are compactified, rolled into intricate, microscopic shapes at every point in space. Primordial black holes could be the ultimate probes for this hidden architecture. Their intense gravity does not just warp the space we know, it might also reach into these unseen realms. Imagine a black hole's gravitational field as a pool of water spreading across a flat surface. Now picture that surface is not flat at all, but has tiny, extra grooves and channels. Some of the water would inevitably seep into those hidden pathways. In the same way, a primordial black hole's gravity could leak into the extra dimensions. This leakage would have a direct and observable effect. It would make the black hole appear to evaporate faster than our standard models predict. We would see a tiny black hole vanish in a flash of Hawking radiation that is just a little too bright, a little too quick. The specific details of that evaporation are the key. The rate at which it loses mass and the precise spectrum of particles it emits in its final moments would act like a complex password, revealing the number of extra dimensions and even their size and shape. A black hole evaporating in a universe with one large extra dimension would look different from one in a universe with 7 tightly wound dimensions. Finding a primordial black hole with the right mass and evaporation signature would be like stumbling upon a universal key. It would not just confirm their existence, it would crack open a window into a reality with more layers than we ever dreamed possible, giving us our first experimental glimpse into the physics that governs the entirety of the cosmos. These cosmic gateways might offer shortcuts across the universe. The fabric of space-time could be punctured not just by black holes, but by bridges connecting two distant points, theoretical tunnels known as wormholes. According to Einstein's equations, such structures are possible, but they have a fatal flaw. A natural wormhole would be incredibly unstable, pinching shut into a singularity the instant anything, even a single photon, tried to pass through. To become a traversable tunnel, a wormhole needs a mysterious substance known as exotic matter. This is not antimatter or dark matter, but something truly strange, a form of energy that creates negative pressure, effectively propping the wormhole's throat open against the crushing force of its own gravity. This is where primordial black holes enter the picture as a potential solution. The extreme quantum fields surrounding a tiny, ancient black hole could theoretically generate the precise conditions needed for this exotic matter. The violent fluctuations at its event horizon, the same processes that drive Hawking radiation, might produce a stable region of negative energy density. Imagine a single asteroid-mass primordial black hole, its quantum aura acting like a cosmic keystone, holding open the entrance to a tunnel that stretches across light years. If a second such black hole existed at the far end, its own quantum fields could stabilize the other side, creating a complete and stable bridge through the cosmos. This is, of course, one of the most speculative ideas in theoretical physics. The properties of the primordial black hole would need to be exquisitely fine-tuned, its mass and quantum state aligning in a perfect, almost impossible harmony. Yet the sheer possibility is breathtaking. It transforms these ancient relics from mere gravitational pits into potential linchpins for interstellar travel. Each one drifting in the dark could be more than a fossil, it could be a locked door, and we are only just beginning to search for the key. The accelerating expansion of the cosmos might be fueled by the death of its smallest ghosts. Dark energy, the mysterious force pushing galaxies apart, has remained isolated from other cosmic puzzles. Yet a radical idea connects it directly to the final moments of primordial black holes. As these tiny relics evaporate through Hawking radiation, they do not simply vanish. The quantum process that unravels them could generate a subtle form of negative pressure, a repulsive gravity that acts on the fabric of space itself. This is not the gentle push of a breeze, but a fundamental anti-gravity woven into the radiation field. Each evaporating black hole contributes a microscopic dose of this expansive force. Now picture the early universe teeming with countless such objects. As they blink out of existence in a cascade of quantum fireworks, their collective negative pressure adds up. It becomes a cosmic tide, an accumulated push that begins to stretch the universe from within. This single framework offers a breathtaking unification. The same population of primordial black holes could account for the dark matter that holds galaxies together through their gravity, and for the dark energy that tears the cosmos apart through their death. One ancient entity would solve both of the universe's greatest mysteries. The dark ghosts would first build the cosmic structures, their gravity pulling matter into galaxies and clusters. Then, in their final sacrifice, they would provide the energy to drive those structures apart, writing both the creation and the destiny of the universe into their brief, dark lives. This transforms our view of cosmic evolution from a story of separate actors into a single, interconnected drama, where the smallest objects dictate the largest fate. The quantum tremors that gave birth to galaxies also forged the universe's darkest relics. You see, the cosmos did not begin with grand structures, but as a near-perfect smoothness, a sea of energy so uniform that the tiny ripples within it were quantum in nature. These were not waves in a traditional sense, but fleeting, random fluctuations in density, popping in and out of existence at the smallest scales. During the frantic expansion of inflation, the universe acted like a cosmic magnifying glass, stretching these subatomic ripples to astronomical proportions. Most of these stretched ripples were modest in size, the gentle hills and valleys that would later serve as the gravitational seeds for clusters of galaxies. But statistics dictates that in any random distribution there will be outliers. For every million gentle hills, there might be one truly colossal mountain. A quantum fluctuation that was exceptionally large, a random spike of density so extreme that when inflation blew it up, it created a region of space with the mass of a star or a planet compressed into a volume smaller than an atom. The moment inflation ended, gravity took over. For the average gentle hill, this meant a slow, steady accumulation of matter over billions of years. But for that one in a million colossal peak, the outcome was immediate and violent. Its own immense gravity offered no resistance, no internal pressure to hold it up. It collapsed directly, completely, and catastrophically, pinching off a piece of spacetime to form a primordial black hole. This makes each of these black holes a fossilized quantum event. Its mass is a direct measurement of the amplitude of that original, random fluctuation. If we could somehow census the masses of all the primordial black holes in the universe, that collection of numbers would be more than just a list. It would be a histogram of the infant cosmos, a statistical fingerprint of the quantum noise from which everything we see ultimately arose. We would know with precision how common large fluctuations were compared to small ones. This data would be a ruthless test for our models of inflation. Did the early universe bubble and boil with wild, high-energy fluctuations, producing a wide spectrum of black hole masses? Or was it a calmer, more refined process, resulting in only a very specific, narrow range? Finding these dark fossils and weighing them would be like an archaeologist uncovering a perfectly preserved dinosaur bone, giving us a direct, unaltered sample of the universe's first moment of existence. Our search for cosmic missing pieces leads us to the magnetic monopole, a particle that should exist everywhere yet remains stubbornly absent. A magnet, no matter how many times you break it, will always have a north and a south pole. A monopole would be a fundamental particle that is just a north pole or just a south pole all by itself. Our best theories of how the fundamental forces unified after the Big Bang insist these solitary poles must have been forged in incredible numbers. So where did they all go? Primordial black holes offer a clean and final solution. They were the universe's ultimate garbage disposals. In the hot, dense chaos of the first moments, these newly formed black holes would have been constantly sweeping through a sea of exotic particles. A magnetic monopole with its immense mass and unique charge would have been a prime target for capture. Upon encountering a black hole, the monopole would be pulled inexorably across the event horizon, its identity and its charge lost forever inside the singularity. This process would have been astoundingly efficient. Countless trillions of monopoles could have been scrubbed from the cosmos in its infancy, neatly solving the mystery of their modern-day absence. This theory elegantly kills two cosmic mysteries with one stone. The fact that we do not see monopoles today becomes powerful, indirect evidence that primordial black holes do exist and that they have been quietly maintaining the cosmic order since the very beginning. Their gravitational hunger purified the universe, removing a troublesome relic and leaving behind the cleaner, more stable cosmos we observe now. The universe's oldest light is not its only relic. A far more elusive background permeates all of space, a cosmic sea of ghostly particles known as the cosmic neutrino background. These are the neutrinos released just 1 second after the Big Bang, and they outnumber the atoms in the universe by over 1 billion to 1. They are the silent, unseen siblings to the cosmic microwave background photons, and they too could carry the faint scars of primordial black holes. Just as a black hole's gravity bends the path of light, it would also warp the trajectory of these ancient neutrinos. A primordial black hole drifting through this ghostly sea would act like a hidden rock in a flowing stream, creating a subtle wake in the neutrino current. The gravity of the black hole would very slightly alter the energy of any neutrino passing nearby, giving it a tiny gravitational boost or redshift. While a single such interaction is impossibly faint to measure, the cumulative effect of a whole population of these dark objects could potentially create a detectable pattern, a specific statistical distortion in the otherwise smooth distribution of neutrino energies and directions across the sky. Detecting this imprint is a challenge for the far future, as these primordial neutrinos have incredibly low energy, making them all but invisible to our current technology. Future observatories, perhaps using vast arrays of sensors to catch the rare, precise interaction, might one day map this background. If they then find it is not perfectly smooth, if they discover strange ripples and dips in its fabric, it could point directly to the presence of an invisible population of gravitational anchors. This turns the entire cosmos into a more complex detective story. We are no longer just looking for shadows in the ancient light, but for invisible currents in a sea of ghosts, searching for the subtle wakes left by the universe's first dark sailors. Our universe may be filled with ghostly superpartners we cannot see. One of the most elusive is the gravitino, the theoretical supersymmetric partner of the graviton, which is the hypothetical particle that carries the force of gravity. In the elegant yet unproven framework of supersymmetry, every known particle has a heavier, shadowy twin. The gravitino would be the superpartner to the graviton, and under certain conditions, it becomes a perfect candidate for the mysterious dark matter. This is where the story of primordial black holes takes a fascinating turn into the world of high-energy particle physics. The presence of gravitinos in the very early universe could have fundamentally altered its behavior. These particles, with their unique properties, might have dramatically amplified the tiny density fluctuations present after inflation. Think of the early cosmos as a still pond, and the gravitino as a substance that makes the surface far more sensitive, turning gentle ripples into powerful standing waves. In this scenario, the regions of space that were already slightly denser would have become overwhelmingly so. Their collapse into black holes not just a possibility but an inevitability. The gravitino would act as a cosmic catalyst, ensuring that primordial black holes were forged in incredible abundance. This theory forges a direct and profound link between the quest to unify the fundamental forces and the existence of the universe's oldest dark objects. It suggests that the search for primordial black holes is not just a study of gravity and cosmology, but also a hunt for evidence of supersymmetry itself. Finding a population of these ancient black holes with the right properties could be the first indirect proof that this elegant symmetry is woven into the fabric of reality, and that the dark matter holding galaxies together is made of gravitinos, the silent partners of gravity itself. Deep within the crushing density of a neutron star, a darker heart may be beating. These hybrid objects, known as black hole neutron stars, begin with a cosmic capture. A primordial black hole with the mass of a mountain drifts too close to the city-sized stellar remnant. It does not collide in a flash, but is instead ensnared by the neutron star's immense gravity, pulled down through its outer layers and settling silently into the core. This is where the slow consumption begins. Nestled in the center, the black hole starts to feed on the surrounding neutron-rich material, a super-dense fluid known as nuclear pasta. The process is not explosive, but a steady, relentless accretion. The black hole eats from the inside out, its event horizon slowly growing as it converts the neutron star's mass into its own. The entire star is being hollowed out, its structure fundamentally altered by a parasite at its very center. This internal decay would leave clear, if subtle, observational clues. A normal, isolated neutron star shines with the residual heat from its supernova birth, glowing fiercely in X-rays for millions of years. But a neutron star with a black hole at its core would be unnaturally cold. The primordial black hole acts as a drain, siphoning away the star's internal thermal energy. The heat generated by the accretion process is swallowed by the event horizon just as quickly as it is produced, leaving almost nothing to radiate from the surface. Astronomers would see a neutron star that appears far too old and cold for its expected age, a dim ghost that has lost its inner fire long before its time. Its spin would also tell a tale. As the black hole consumes the core, the star's moment of inertia changes. This could lead to strange, unpredictable glitches in its rotation, or cause it to spin down much faster than a normal pulsar. These objects would not be rare flashes in the dark, but permanent residents of our galaxy, hiding in plain sight among the population of known neutron stars. We may have already catalogued them, mistaking their profound chill and quiet death for simple old age. Finding one would require a new kind of galactic census, searching not for the brightest beacons, but for the quietest, coldest, and most peculiar stellar remnants, each one potentially masking a cosmic ghost finishing its meal. The dark matter halo surrounding our galaxy may be a vast, drifting ocean of ancient black holes. This theory suggests the invisible mass holding the Milky Way together is not a sea of unknown particles, but a colossal swarm of primordial black holes, each one a silent, dark relic from the first second. Their collective gravity would be the anchor, the unseen hand that keeps stars from flying off into the void as the galaxy spins. Imagine billions upon billions of these objects, ranging from the mass of a small asteroid to that of the planet Neptune, all moving through the immense spherical halo that envelops the visible disk of our galaxy. Their combined pull would perfectly replicate the gravitational effects we attribute to dark matter, yet they would be almost impossible to see directly. This idea elegantly sidesteps the decades-long search for exotic particles like WIMP or actions, proposing instead that the missing mass is made of objects we already know can exist, just in a different and more ancient form. The gravitational influence of this swarm is a matter of sheer numbers. A single asteroid mass black hole, smaller than a pebble yet weighing as much as a mountain, would have a negligible pull on its own. But when you have trillions of them spread throughout the galactic halo, their individual tugs combine into a powerful, smooth gravitational field. This field acts like an invisible scaffold, providing the extra gravity needed to explain the rapid orbits of stars on the galaxy's outskirts. It is a solution built from the bottom up, using the established physics of gravity to explain a cosmic mystery without inventing a new form of matter. However, this beautiful picture faces a serious challenge from years of meticulous observation. Microlensing surveys have spent decades staring at millions of stars in neighboring galaxies, waiting for the telltale flash caused by a compact object drifting in front of them. These surveys have placed strict limits on how many planet mass objects can be floating in the halo. They have largely ruled out the possibility that the entire dark matter halo is made of objects in the mass range of Jupiter or larger. But this is not the end of the story, it is a refinement. The microlensing constraints have effectively closed certain mass windows, but they have also pointed us toward the gaps that remain wide open. The most promising window for primordial black holes as the primary dark matter constituent now lies at two extremes. The first is the lower end, with black holes smaller than an asteroid, masses comparable to a large mountain or even less. These are too light to create a noticeable microlensing event that our current surveys can reliably detect. The second window is at a higher mass, in the range of Earth to Neptune mass black holes. Objects this heavy are so rare that their microlensing events would be incredibly infrequent, happening only once every few decades for a given star, making them very difficult to rule out with current data. This means the galactic halo could still be teeming with these ancient ghosts, either in vast numbers of incredibly tiny specks or in a smaller population of heavier, planet-sized dark giants. The hunt is now more focused than ever, a cosmic search not for one answer, but for a specific signature that fits within the cracks of our existing data. The halo remains a mystery, but it is a mystery with a potential solution written in gravity itself, a solution waiting for the right observation to bring its dark constituents into the light. A thin, dark disk of ancient black holes might be cutting through our galaxy. This is the double-disk dark matter model, a theory that splits the cosmic shadow into two distinct components. Imagine the Milky Way not just wrapped in a spherical halo of invisible matter, but also containing a dense, pancake-thin disk of primordial black holes, aligned with the familiar plane of stars, gas, and dust. In this picture, dark matter is not one single mystery, but two. The traditional spherical halo remains, potentially composed of the long-sought, weakly interacting massive particles, or WIMP. These are the ghostly subatomic particles that barely touch normal matter. But then there is the second disk, a separate structure made entirely of primordial black holes that have settled into the galactic plane over billions of years, just like the visible stars. Why would these two dark components separate? It all comes down to interaction. WIMP by their very definition, hardly interact with each other or with normal matter. They can maintain a vast, puffy halo, but primordial black holes are different. As they orbit, they can gravitationally nudge each other and feel the drag from the galaxy's gas. This friction causes them to lose energy over cosmic time, slowly sinking from all directions to congregate in the thinnest, densest part of the galaxy, its central disk. This model was born from a terrestrial mystery buried deep in Earth's geological record. Scientists studying the timing of major impact craters found a surprising pattern, a potential periodicity in asteroid and comet strikes stretching back hundreds of millions of years. What could possibly cause regular comet showers? The answer might lie with that dark disk. As our solar system orbits the galaxy, it does not move in a perfectly flat circle. It bobs up and down, weaving through the galactic plane like a horse on a carousel. Every 30 million years or so, our entire planetary system plunges through that hypothetical disk of primordial black holes. During that passage, the collective gravity of this dark swarm would stir up the icy bodies in the distant Oort cloud, a vast shell of comets at the solar system's edge. This gravitational jostling would dislodge countless comets, sending a shower of them hurtling inward, some of which would inevitably cross Earth's path with devastating consequences. The double disk model elegantly ties together the cosmic and the terrestrial. It links the grand architecture of our galaxy's dark components to the very real scars on our own planet, suggesting that the rise and fall of species over geological time might be orchestrated by the silent, rhythmic passage of our world through a sea of ancient ghosts. The universe's first black holes may not have been born alone. In the dense, turbulent environment of the early cosmos, two primordial black holes could have formed in close proximity, instantly locking each other in a gravitational embrace. These pairs are the primordial black hole binaries, cosmic couples whose fate was sealed from the very first moment. Their initial dance was likely a chaotic one, set against a backdrop of rapidly expanding space and the gravitational pull of surrounding matter. But once the universe grew large enough to thin out this cosmic crowd, the pair was left to its own devices, bound together by their mutual gravity and destined for a slow, stately spiral towards a final collision. This long, silent waltz is driven by a relentless loss of energy. As the two black holes orbit one another, they churn the very fabric of space-time, sending out ripples known as gravitational waves. This emission acts like a cosmic brake, constantly sapping the system's orbital energy. With each passing orbit, the black holes lose a tiny bit of speed, drawing them imperceptibly closer together. Over billions of years, this slow, steady decay shrinks their orbit from a vast separation to a final, frantic merger. The rate at which these mergers happen is a crucial piece of the puzzle. Physicists can calculate how many such pairs should have formed in the early universe and how many would be reaching the end of their inspiral today, based on what fraction of dark matter is made of primordial black holes. If these objects were a dominant component of dark matter, the sky should be ringing with the constant chirps of their mergers. This is where our gravitational wave observatories become powerful cosmic census takers. LIGO and Virgo are listening to the universe, and they provide a real number, a count of how many black hole mergers we actually detect within a certain volume of space over a given time. By comparing the observed merger rate with the predicted rate from primordial binary models, scientists can place strict limits on the population. If the predicted rate from a model where all dark matter is primordial black holes is 1,000 mergers per year, but we only see 10, then that model is overwhelmingly ruled out. This comparison has already closed the door on primordial black holes making up all of dark matter across a wide range of masses. The silence of the cosmos, punctuated only by the occasional detected merger, tells a story of scarcity. It suggests that if these ancient relics do exist as a significant part of the cosmic dark matter budget, they must be either very light or very heavy, occupying the mass windows where their binary mergers would be too faint or too infrequent for our current instruments to confidently rule out. Each new gravitational wave detection is not just a discovery, it is a data point in this ongoing investigation, refining our understanding of what the dark universe is truly made of. These silent cosmic engines may have actively sculpted the cosmic dawn. Primordial black holes were not passive inhabitants of the early universe, they were dynamic agents of change, their feeding habits capable of reshaping the entire environment around them. This is the theory of accretion-driven feedback, a process where the energy released by a black hole's meal fundamentally alters its own future food supply. Imagine a primordial black hole drifting through a cloud of pristine hydrogen gas in the infant cosmos. As gas particles spiral inward, drawn by the relentless pull of gravity, they do not fall silently. They collide with each other at ferocious speeds, converting their immense kinetic energy into a blazing torrent of heat and light. This process creates a brilliant, hot bubble around the black hole, a region where the temperature soars to millions of degrees. Now, this superheated gas does not want to fall in. It fights back with tremendous outward pressure, creating powerful winds and outflows that blast away from the black hole at nearly the speed of light. These outflows act like a cosmic broom, sweeping through the surrounding gas clouds, the very raw material needed to build the first stars and galaxies. The gas is either heated so much that it cannot easily cool and condense, or it is physically pushed away into the void. This feedback process could have had a devastatingly efficient effect on the smallest proto-galaxies. A fledgling galaxy trying to coalesce near one of these active black holes would find its gas reservoir evaporated or expelled before it could even form its first star. The black hole's hunger would effectively starve its smaller neighbors, stunting their growth or preventing them from forming altogether. This would leave a permanent scar on the cosmic landscape, an imprint on the large-scale structure of the universe. We might see this today as a surprising scarcity of very small, faint dwarf galaxies orbiting larger ones. The feedback from countless primordial black holes could have systematically pruned the bottom branches of the galactic family tree, altering the entire hierarchy of structure formation. It means the universe we see today, with its specific distribution of giant galaxies and their smaller satellites, may have been decisively shaped by the violent breakfasts of the cosmos's oldest and darkest ghosts. The early universe was a battlefield between gravity and light. Before the first stars even flickered to life, a relentless struggle played out in the primordial plasma, a searing hot soup where photons and matter were locked in a tight embrace. This cosmic conflict set a fundamental limit, a minimum size for any structure that could hope to survive. This limit is known as the Silk damping scale, named for the physicist Joseph Silk, and it nearly erased the smallest building blocks of the cosmos before they could even form. The mechanism was brutally efficient. Imagine a tiny knot of density trying to form, a region where gravity was just beginning to pull matter together. In that dense plasma, photons exerted an immense outward pressure. As the clump tried to contract, these photons would simply scatter off the particles, pushing them apart and smoothing out the overdensity. It was a cosmic iron, pressing the wrinkles out of the fabric of space before they could become permanent. This photon pressure effectively erased all small-scale fluctuations below a certain mass, washing away the potential seeds for the tiniest galaxies and star clusters. But there was a narrow window of opportunity, a fleeting moment for certain fluctuations to escape this damping. The key was the horizon, the maximum distance light could have traveled since the Big Bang. In the very first instance, the cosmic horizon was incredibly small. A density fluctuation that was just the right size to enter this horizon before the universe had cooled enough for the photon pressure to become overwhelming could have collapsed without being smoothed away. For a brief time, gravity could win. The fluctuation would cross the horizon, and inside its own little causal bubble, it would be free from the homogenizing influence of the outside photon bath. With nothing to stop it, this super-dense region would collapse directly into a primordial black hole. This elegant escape hatch creates a very specific prediction. The mass of a black hole formed this way is directly tied to the horizon mass at the moment it crossed that threshold. This gives us a precise, calculable mass range for these particular silk-damping escapees. They are not scattered randomly across all possible weights, but are predicted to cluster around a specific value, roughly between 10,000 and 100,000 times the mass of our Sun. This is a profound target for astronomers. Instead of searching the entire gravitational spectrum for any hint of a black hole, we can now focus our efforts on this specific mass window. It tells gravitational wave observatories what frequency of merger to listen for with extra sensitivity. It informs microlensing surveys about the duration of lensing events they should prioritize. This theory transforms a complex piece of early universe physics into a concrete hunting guide. We are no longer searching for a ghost in the machine, but for an object with a specific mass that left a specific fingerprint on the cosmos. The very process that tried to erase the small-scale structure of our universe may have, in its failure, created the perfect dark fossil for us to find. The universe's first black holes could be frozen drops of a fundamental field. Cue balls offer a particle physicist's recipe for creating a singularity, a process that begins not with gravity, but with a strange and stable knot in the fabric of reality itself. In the theories that extend beyond the standard model, particularly in supersymmetry, the cosmos might be filled with exotic scalar fields. Under the right conditions, a pocket of this field can become charged, twisting in upon itself to form a coherent, self-sustaining object. This is a cue ball, a non-topological soliton. Think of it not as a particle, but as a dense, stable blob of pure field energy, a bubble of an alternative state of vacuum that refuses to pop. It is a cosmic drop of dew, holding its shape against the pressure of the surrounding universe. For a cue ball to transform into a black hole, it simply needs to grow too heavy for its own good. As it rolls through the early universe, it could absorb more of the scalar field charge, growing in mass and density. There is a critical threshold, a point of no return where its self-gravity becomes overwhelming. Once that line is crossed, the cue ball can no longer maintain its delicate internal balance. Its own gravitational pull triggers a catastrophic collapse. The entire object, a concentrated lump of energy that may have spanned a solar system, would implode in a flash, wrapping a region of space so tightly that a primordial black hole is the only possible remnant. This theory creates a breathtakingly direct bridge between the abstract world of high-energy particle theory and the tangible gravitational giants we detect across the cosmos. The properties of the resulting black hole become a direct fossil of the underlying particle physics. Its mass would be determined by the charge and stability of the parent cue ball, potentially creating black holes with very specific weights, a distinct signature that could one day be spotted in the data from gravitational wave observatories. Finding such a pattern would be more than just discovering an ancient black hole. It would be like finding a manufacturer's tag, revealing that the object was forged not from a random density fluctuation, but from a precise and exotic particle phenomenon, offering us a direct glimpse into the laws that govern reality at its most fundamental level. Another class of cosmic defect could have forged these ancient relics. While cosmic strings are like one-dimensional cracks in space-time, domain walls are their two-dimensional cousins. Imagine the early universe cooling, its fundamental fields settling into new states, like water crystallizing into ice. Sometimes the field gets stuck between two equally valid states, unable to decide. At the boundary between these two different domains, a vast sheet-like structure forms, a domain wall. This is not a physical wall you could touch, but a flaw in the vacuum itself, a membrane of concentrated energy stretching across the cosmos. These walls would have been unimaginably dense, with a single square inch potentially containing more mass than our entire planet. Such a structure cannot last. Under its own colossal tension, a large curved section of this domain wall would be driven to collapse. Picture a gigantic, flimsy sheet of rubber being pulled from all edges at once, crumpling into an ever smaller, denser knot. As the domain wall crumples, the energy once spread across a vast area becomes concentrated into a vanishingly small point. The density soars to infinity, and space-time itself gives way, pinching off to form a primordial black hole. This violent birth leaves a distinct fingerprint. Unlike black holes formed from random density fluctuations, which could have a wide spectrum of masses, the children of a domain wall are all nearly identical. The mass of the resulting black hole is determined by a single property, the energy scale of the underlying physics that created the wall in the first place. Every collapse of a similar domain wall would produce a black hole of the same mass, like a factory stamping out identical cosmic products. This creates a very specific prediction for astronomers. We would not expect to find a smooth distribution of black holes of all sizes, but a sharp, narrow spike at one particular mass. If our gravitational wave detectors or microlensing surveys ever find a surprising overabundance of black holes all weighing, for example, exactly 1,000 solar masses, it would be a stunning clue. Such a discovery would point directly to this exotic origin, proving that the universe's first structures were not just clumps of matter, but literal tears in the fabric of reality, whose collapse seeded the darkness we now seek to find. The hidden geometry of reality itself might have forged the universe's first black holes. String theory's vision of a cosmos with tiny, curled-up extra dimensions requires a set of master architects' scalar fields known as moduli. Each moduli field acts like a cosmic dial, fixing the size and shape of one of these unseen dimensions. For our universe to be stable, these dials needed to settle into specific, stable values after the inflationary frenzy. But this settling process was anything but calm. As the moduli fields rolled down their complex energy landscapes towards stability, they began to oscillate wildly. Think of a ball bouncing down a steep, rocky hill, ricocheting off bumps and divots with tremendous energy. In the dense, hot environment of the early cosmos, these frantic oscillations could have become unstable. The field began to fragment, breaking apart not into particles, but into coherent, vibrating lumps of pure energy. These are oscillons, or their more stable cousins, cue balls. An oscillon is not a particle in the traditional sense, but a soliton, a self-reinstanding wave packet that holds its shape like a knot in the fabric of the field itself. These knots would have been incredibly dense, acting as localized concentrations of mass energy sprinkled throughout the newborn universe. Each one was a potential seed for a far greater darkness. The fate of an oscillon hinges on a simple, brutal calculation of gravity versus pressure. Could the oscillon's internal forces resist the pull of its own immense density? For the largest and heaviest of these knots, the answer was no. Their self-gravity would have overwhelmed all other forces, triggering a catastrophic collapse. The oscillon would have imploded, its energy concentrating into a point so dense that it wrapped space around itself, spontaneously giving birth to a primordial black hole. This theory does more than just add another creation mechanism to the list. It embeds the origin of primordial black holes directly into one of our most ambitious attempts to unify all of physics. The properties of these black holes, their masses and their potential abundance, become a direct reflection of the moduli fields and the geometry of the hidden dimensions they control. Finding a population of primordial black holes with a specific, predicted mass could be our first experimental hint that string theory is correct, that the universe truly is built upon the subtle vibrations of multidimensional strings. These dark relics would be more than ancient fossils. They would be crystallized notes from the symphony of creation. each one a frozen echo of the moment the extra dimensions snapped into place. The universe's first moments were a delicate thermal dance, a precisely timed sequence that forged the very atoms we are made of. This process, known as Big Bang nucleosynthesis, is one of the great successes of modern cosmology. Its predictions for the amounts of hydrogen, helium, and lithium created just minutes after the Big Bang match our observations of the oldest cosmic gas clouds with astonishing accuracy. This perfect agreement, however, rests on a critical assumption that the universe expanded and cooled in a smooth, predictable way, free from major disturbances. A population of primordial black holes would have been the ultimate disruptors, injecting chaos into this fragile nursery. Each black hole from its birth was a point of immense gravitational influence. As it moved through the primordial plasma, it would have pulled in surrounding hydrogen and helium, compressing and heating this material in a frantic accretion disk. This process does not just hide matter, it converts gravitational energy into a blaze of radiation, from X-rays to potent gamma rays. This is not a gentle warmth, it is a torrent of high-energy particles flooding the environment. If too many of these objects existed, they would have effectively reheated the cosmos. Think of a carefully cooling oven suddenly filled with a network of blowtorches. The delicate balance of particle interactions that allowed protons and neutrons to assemble into the first light elements would have been shattered. The extra heat and radiation would have broken apart deuterium nuclei as quickly as they formed, altering the final cosmic recipe. We would see a different abundance of helium in the oldest stars, or a complete absence of lithium, compared to what we actually observe. The fact that the predictions and observations align so perfectly is a silent yet powerful testimony. It tells us that the infant universe could not have been teeming with these energetic ghosts. The thermal history of the cosmos acts like a cosmic logbook, and its entries rule out a universe dominated by primordial black holes during its first few minutes. This places incredibly tight constraints on their possible population, effectively closing the door on certain mass ranges and abundances. The very success of Big Bang nucleosynthesis forces these ancient black holes into the shadows, allowing them to exist only in numbers small enough to have left the universe's primordial kitchen undisturbed. This cosmic hum is the collective whisper of countless ancient mergers. While observatories like LIGO catch the loud, distinct chirps of individual black hole collisions, the universe is also filled with a far more subtle sound, a stochastic gravitational wave background. This is not a single event you can pinpoint, but a random, persistent noise, the acoustic equivalent of hearing the roar of a distant ocean, made up of every wave crash that has ever happened. If primordial black holes exist in vast numbers, their entire history of merging would contribute to this universal static. From the very first binary pairs that formed in the infant cosmos to the random captures happening in dense clusters today, each merger sends its own tiny ripple into the fabric of spacetime. Alone, each ripple is far too faint to ever discern. But together, across billions of years and countless collisions, they combine into a diffuse, all-pervasive hum that fills the universe. This background is the integrated story of primordial black hole interactions, a fossil record written not in stone, but in the vibrations of space itself. The properties of this hum are a direct message from the hidden population. Its amplitude or loudness tells us how many of these mergers have occurred, which reveals the overall abundance of primordial black holes. A louder hum means a more crowded cosmos filled with more frequent collisions. Even more revealing is the frequency of this hum. The pitch of a gravitational wave is tied to the mass of the objects merging. The merger of two incredibly heavy black holes produces a low-frequency rumble, while the union of two light ones creates a high-frequency chirp. A population of primordial black holes with a specific preferred mass would therefore imprint a distinct peak in the background noise, a dominant note in the cosmic chorus. This is where future observatories like LISA, the Laser Interferometer Space Antenna, come in. LISA will be a fleet of satellites orbiting the Sun, forming a gravitational wave observatory with arms millions of kilometers long. This vast scale will make it exquisitely sensitive to the low-frequency waves that LIGO cannot hear, the very frequencies where the collective hum of a primordial black hole population should be strongest. By listening to this stochastic background, LISA will not just confirm its existence, it will decode its spectrum. It will measure the precise range of notes in the hum, translating that data directly into a census of the black holes that created it. We will learn their dominant masses and their total numbers across cosmic history. This faint, random noise could become the clearest voice yet, telling us if our universe is truly filled with these ancient dark ghosts. A star could burn for eons without a single atom fusing in its core. This is the strange reality of a primordial black hole-powered star, a structure where the very definition of a star is rewritten. Instead of the tumultuous nuclear furnace that drives our sun, the engine at the heart of this star is a dark, ancient singularity. The formation is elegantly simple. In the early universe, a wandering primordial black hole, perhaps with the mass of an asteroid, drifts into a vast, cold cloud of primordial hydrogen and helium. Its gravity immediately begins to pull the gas inward, but unlike a simple collapse, the gas does not fall silently into the abyss. As it spirals toward the event horizon, it is compressed and heated to incredible temperatures, generating a steady, fierce glow from accretion. This radiant energy pushes outward, creating a delicate and perfect balance. The inward crush of the surrounding gas cloud is exactly countered by the outward pressure of the heat from the black hole's meal. This equilibrium allows a massive, stable star to form, with the primordial black hole sitting at its center like a hidden pilot light. The life cycle of such an object would be alien to everything we know about stellar evolution. A fusion-powered star lives a frantic, brilliant life, doomed to explode or fade in a relatively short cosmic time. But a PBH-powered star is in no such hurry. Its energy source is not the consumption of finite nuclear fuel, but the relentless, slow conversion of gravitational potential energy from the infalling gas. As long as there is ambient material to feed the central black hole, the star can continue to shine. It could, in theory, burn for trillions of years, far outliving any conventional star and potentially surviving from the cosmic dawn until the present day. This leads to a breathtaking possibility. Our galaxy could be hiding these dark-hearted stars right now, camouflaged among the billions of other points of light. They would not look like a brilliant blue or white young star, nor a cooling red dwarf. Their light would be strange, emanating from the intense heat of the accretion disk rather than a broad fusion spectrum. They might appear as unusually cool, yet massive and long-lived objects, their quiet, persistent glow a testament to the dark engine beating within them. Finding one would be like discovering a living fossil from the first chapters of the universe, a star that defies the standard rules of physics and shines with the borrowed light of a cosmic ghost. The evaporation of a black hole is a ticking time bomb for the laws of physics. At the heart of this crisis is a principle called unitarity, a sacred rule of quantum mechanics that insists information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. Now picture a book thrown into a stellar black hole. According to Einstein's general relativity, the book and all the information printed on its pages is lost forever behind the event horizon, eventually crushed into the singularity. When the black hole finally evaporates via Hawking radiation, all that remains is a faint, random thermal glow, a formless heat that carries no details about the book's title, its author, or the words it contained. The information is gone and unitarity is shattered. This is the black hole information paradox, and for a massive black hole, it remains a distant philosophical problem. But for a small primordial black hole nearing the end of its life, this crisis is immediate and explosive. Its final, brilliant flash of Hawking radiation is the very moment where our understanding of reality could break down. To rescue quantum mechanics, physicists have proposed some truly radical solutions. One idea is the final state projection hypothesis. This suggests that at the instant a black hole forms, a unique quantum law is imposed on its singularity, a rule that acts like a cosmic editor. As the black hole evaporates, this editor ensures that the Hawking radiation leaking out is not random noise, but is subtly entangled with the information that fell in long ago. The information is not lost inside, but is instead projected onto the outgoing radiation, perfectly preserving it. Another, even more dramatic proposal is the firewall hypothesis. It claims that to save unitarity, the event horizon cannot be the smooth, empty space Einstein predicted. Instead, it must be a blazing wall of ultra-high-energy particles, a literal ring of fire. Any object falling in would be incinerated the moment it touches the horizon, its information immediately encoded onto this fiery boundary and then released with the Hawking radiation. A primordial black hole is the only place in the universe where we could hope to test these mind-bending ideas. Its entire life cycle, from birth to explosive death, plays out on a timescale where these quantum gravitational effects become dominant. If we could ever detect one of these tiny black holes in its final evaporation, we would analyze the spectrum of its last gasp with incredible precision. Is the radiation truly random and thermal, as Hawking first calculated, which would mean information is lost and physics is flawed? Or does it contain subtle, hidden correlations, tiny deviations from perfect randomness that whisper the story of what the black hole consumed? Finding even the faintest pattern in that final flash would be a revolution. It would validate one of these wild theories and prove that the universe at its most fundamental level is logical and predictable. These ancient cosmic ghosts are not just fossils, they are the ultimate arbiters in a debate that will define the future of physics itself. The final theory pulls the lens back to the very end of time. In a future so distant it defies comprehension, when the last star has flickered out and the cosmic background glow has faded into a whisper, the universe will be a cold, dark, and profoundly empty place. Galaxies will have evaporated, their stars either burned out or flung into the intergalactic void. In this era of eternal twilight, the only significant structures left might be these ancient primordial black holes. They would be the final monuments, the last macroscopic objects adrift in an expanding sea of nothingness. Their enduring gravity, a silent echo from the first second, would be the only force still capable of holding anything together in a universe nearing maximum entropy. For trillions upon trillions of years, they would be the sole landmarks in an ocean of darkness, outliving every star, every planet, and every galaxy. Their reign would not be eternal, however. In this frozen cosmos, the slow, quantum whisper of Hawking radiation would become their undoing. Isolated and with nothing left to consume, each black hole would begin to lose mass, a process achingly slow for the larger ones but inexorable. One by one, they would enter their final death throes. The evaporation of a typical primordial black hole would be one of the last energetic events in the entire cosmos, a brief, brilliant flash of particles and radiation punctuating the overwhelming silence. Imagine the very last primordial black hole, a relic from the dawn of creation, finally dissolving in a final burst of light. That last spark would mark the end of an era, the moment when the last object born from the Big Bang vanishes from existence. What remains is a universe so cold and dilute that even the concept of time may lose its meaning, a vast, silent expanse containing only a thin, cooling sea of fundamental particles and radiation drifting forever apart. This ultimate fate casts these dark ghosts in a poignant new light. They are not just the potential builders of the cosmos, but also its final sentinels, witnessing the entire cosmic story from its violent birth to its quiet, frozen end. From dark matter to dark energy, from the cosmic web to the final flash of Hawking radiation, we have journeyed through 50 mind-bending possibilities for these ancient cosmic ghosts. The sheer scope of these theories reveals just how fundamental primordial black holes could be, touching upon nearly every great mystery in modern physics. They are not just one potential answer, but a key that could unlock a dozen different doors, revealing the hidden architecture of everything from the smallest quantum scales to the vastest cosmic structures. This grand hunt, combining the precision of gravitational wave astronomy, the patience of microlensing surveys, and the brilliance of theoretical insight, stands as one of the most thrilling scientific frontiers of our time. To confirm their existence would be more than just adding a new object to the cosmic catalogue. It would be a paradigm shift, forcing us to rewrite the story of the universe from its very first second. It would connect the quantum birth of reality to the gravity that shapes it, offering a unified narrative for our cosmos. So the next time you gaze into the deep, dark sky, remember that the emptiness between the stars might not be empty at all. It could be shimmering with the gravity of 1 billion ancient relics, each one a silent testament to the universe's violent and mysterious beginnings. We would love to hear which of these 50 theories captured your imagination the most. Share your favorite cosmic possibility in the comments below. And if you are hungry for more journeys to the edge of our understanding, be sure to subscribe for our next deep dive into the universe.